Further, you guys tell me, how is the sound produced by we humans?
Through the vocal cords.
Vocal cords. How will be the vocal cord producing sound? How does it produces sound? Yes. Basically produces sound by vibrating now. It will be producing sound by vibrating. Okay. And the length of the vocal cord is more in the male or in the female?
Male.
In the male. What is the length, average length of the vocal cord in the male is?
20 millimeter.
20 millimeter. Very good. And in the female it is?
15 millimeter.
15 millimeter. Very good. So we have learned how the sound will be produced in this. We did also learn about how the sound will be propagating through a medium, how it will be moving. Okay. Sound will always require a medium to travel from the surface, from the source of its production to the place where it will be received. And different mediums in which it can travel was basically air, liquid, or solid. In the case of we did compare the speeds also. We learned that sound through the water travels 4 times faster than through the air, and sound through the solids travels 13 times faster than the air. So the speed of the sound is maximum in solid. That is something which we have done. Okay. Okay. Before we continue further, we are going to solve one numerical question, and then we'll be learning about the concept of the sound. Okay, now. So let's say that there's a man who hears the thunder 5 seconds after the lightning is seen. You know the speed of the light is more as compared to the sound, right?
Yes, sir.
Like the speed of the sound in air is about 340 meter per second. The speed of sound in the air is about 340 meter per second. Let me write this. The speed of sound in the air, it is 340 meter per second. But as compared to this, we know that the speed of light is about 3 lakh kilometer per second. Right now, 3 lakh kilometer per second. So there's a huge difference. That's why first you will be seeing the lightning and then you hear the sound of the thunderstorm, right? So suppose there's a question, a man hears the thunderstorm, hears the thunder 5 seconds after the lightning is seen. Okay. So question is, how far is the lightning from the man? How far that lightning is from the man? If the sound of if the speed of sound in air is, let's say, 330 meter per second or 340 meter per second. Let's take 330 meter per second for this question. So if the lightning is seen after sound is heard after 5 seconds of the lightning. So the further question is that how far is the lightning from the man if the speed of sound in air is 330 meter per second as per the question. Okay. Also, this 340 meter per second, it's the average speed of sound in the air. It may vary. It may vary depending upon the temperature and the humidity of the air. Getting it now? Later on, we will be learning about this also. What factors will influence the speed of the sound? As of now, you guys
20.
repeat again.
It is 1020 meter far.
No, not that much. No. Let me just draw a small diagram here. So say that this is the place where the lightning has occurred, where the thunderstorm is observed. So this is the thunder, basically lightning here. Lightning is occur, and because of which thunder is also produced. So let's say there is a man standing over here. Okay. And the sound would have traveled to this man. And the speed at which it traveled, as per the question, what is the speed of the sound given as per the question? 330 meter per second. Good. 330 meter per second. So you have to calculate the distance. How far that man is from the thunder. You guys know about the basic formula to calculate the distance, to calculate the speed and time, etc.
Yes,
Isn't it?
yes.
Using the formula, just calculate it. As simple as that. Speed is basically measure of what we know about speed. Speed is basically measure of how fast or how slow an object is moving. Okay. And you know the speed of the formula of the speed. Speed equals to what is the formula to calculate the speed, by the way? Right now we are not required to calculate the speed, but generally I'm asking what is the formula to calculate the speed?
Speed is equal to time by distance.
No,
So distance by time.
distance by time. So speed equals to distance upon time. But in the question, we are not required to calculate the speed. It is already given, right? Time is also given here. We are required to calculate distance. So can we write that distance equals to speed into time?
Yes, sir.
You all would have learned about this. So time is given here, 5 seconds, and speed is also given here. That is 330 meter per second. You just have to calculate the distance. By now, you should have already got the answer. Yes.
So I got it.
Yes. What is it? Tell me.
Sir, I've sent it.
Write the unit also, Shukrika.
I'm getting 1,700.
Write in the no, that is not correct. Write down the answer in the chat box, all of you. Since everyone is doing this, also all of you turn your cameras on in the class now. I don't like saying this simple thing again and again.
Sir,
Yes.
so that is a meter per second, right?
Yeah, it's
That-
meter per second.
Okay.
Meter per second. Yes, Khadija, very good. Khadija, Chakrika, you guys have got the answer. Good. Abdullah, you are not doing some error in the multiplication, I guess. That's why you're not getting the right answer. Chakrika, wait a minute. It's distance now. How can unit be meter per second? It will only be meter. Okay. Now it is correct. Roni, you there in the class? Yeah, you are there. Gauri, what happened to you guys? Speed into time. Speed as per the question is 5 meter per second. And here the time given is 5 seconds. So this second cancel. 1 minute. Speed is okay, 330 meter per second. No, sorry, 330 meter per second, that is given here. So this second unit will be getting cancelled. You are simply multiplying 330 with 5. So 330 multiplied 5 will be 1650 meter. Hope everyone got this. Okay. So that is something which we have done.
Using that only. 1,600.
Okay, good then. Later on, we will also learn about echo also, and in there also we'll be doing some questions on this. Okay. Okay. So far we have learned about some of the important things. Let's continue further. Now we are going to learn about the wave. So the thing is that if we were to talk about the wave property of the sound, it basically says that sound is a type of sound will be traveling in the form of waves, right now. So it will be traveling through a medium by creating alternate areas of compression and rarefactions. It will be moving through a medium by producing alternate compression and rarefaction, as you guys can see here. Okay, now in this, what is happening? The particles are getting pushed together at some places, and at some places the particles are being pulled apart, as you guys can observe here. Yes, like here the particles are being pulled away from each other. Here they are being pushed close to each other.
Yes.
Right? This expansion, compression, expansion is basically rarefaction. That is one thing. Further, you guys can see here, I have taken the picture of this transverse waves also. So this I have taken to tell you that there are two types of waves. Like there are two types of wave, and sound is a longitudinal wave. Sound travels in the form of longitudinal waves. There is another kind of wave also that is called as transverse waves. This you can understand, for example, when you guys throw a stone in in pond or in a calm water, the water that is not moving. So ripples forms in that, isn't it? Ripples forms like this
Yes.
circular ripples will form. So when there you will look at the water will be moving in a wavy fashion. It moves in the wavy fashion and it moves in the forward direction. So the movement of the ripples in the form of the crest and in the form of the trough, like this, in the form of the crest and the form of trough. So that is called as transverse waves. That is the concept of the transverse waves. Okay. So what I'm saying that there are two types of waves, longitudinal and transverse waves. And sound is which one? Sound travels in the form of transverse or the longitudinal?
Yes, sir.
Sound travels in the form of longitudinal waves, right? So in longitudinal waves, what we're getting to see here, that the sound is traveling in this medium through, it is moving through the medium by by creating alternate areas of compression and rarefaction. And here you will see that the particles at some places are being pushed together and at some places they are being pulled apart. And it is happening in an alternate manner. Okay, na? Like there is one compression, one rarefaction, one compression, one rarefaction. Like here you see, there is one expansion or rarefaction, and then there is compression. Then again rarefaction, then compression, rarefaction and compression. So isn't this happening in an alternate manner, in an alternate fashion? Getting it, guys? So that is what we are learning here, that sound travels in the form of waves. Okay, no? Also, we have learned how the sound is produced. It is produced by the vibration of the objects. And they will be traveling from one place to another in the form of waves. Hence, we call this as the sound wave also. Like see in this image, the string of the guitar is vibrating. Because of that, the air particles around it will start to vibrate now. The air particles will start to vibrate and it will be vibrating in this fashion. The air particles will vibrate in this fashion. Okay. And the question is, how is the energy being transferred from one source to another? So it is being transferred in the form of the sound waves. Due to the vibration of the particles, at certain places, the particles will come close to each other. At certain places, they are pushed away from each other. And that creates the sound waves. Okay, now? So let me write a few important points here. That sound is a sound travels in the form of longitudinal waves. It travels in the form of longitudinal waves by creating alternate areas of compression and rarefaction. Rarefaction is basically expansion. Another term being used for expansion here. Where what happens? Where the particles are pushed together and then they are pulled apart. Where the particles of medium are pushed together and pulled apart That is one thing. So is this basic concept clear to everyone? If any
Yes,
confusion
sir.
in this, please let me know. Any questions? Yeah, sure. What is happening here? That sound, as we're learning about the sound here, basically the wave nature of the sound. So sound as we have learned, it is produced due to the vibration of the objects. As the object will be vibrating, due to the vibration of the object, the air molecules around it, basically air molecules, we are generally calling this as particle. General term, we are using particle for this molecule basically. So the particles of the medium will vibrate. In this case, the particles of the air will vibrate. And at some places, they will be pushed together. That area will be called as compression. And the place where they are pulled apart, that will be called as expansion. Right now, look back at this animation once again. Here we get to see that the particles at certain places are being pushed together. Then they are being pulled apart, pushed together and then pulled apart. Basically, it's compression and expansion. And because of which the energy is transferred from one place to another. That is one thing. But if you to talk about how it is traveling from here to here, we are seeing that for it to travel, it is traveling in the form of waves. Waves are being formed here. Getting it, guys? Waves are being formed here. So that is the case of the wave nature of the sound. That is the case of the wave nature of the sound. Okay, now. Also, one general thing is that talking about the wave and particle motion here, mechanical waves, they are basically two types of waves. Okay, now. One is the transverse wave, another one is the longitudinal wave. In the case of transverse wave, what we are getting to see that the particles of the medium will be moving perpendicular to the direction of the movement of the wave. Take, for example, the formation of ripples in the water. The formation of the ripples in the water, like this here. Or the traveling of the light waves. Light also travels in the form of waves now. Just take the example of the ripples. So the water particles are moving they are moving perpendicular to the direction of the movement of the wave. Like, for example, this is a lake. This is a calm lake. It is not, the water in it is not flowing, and you have thrown a stone here. So then what will happen? The ripples will start to form now, isn't it? The ripples will start to form.
Yes, sir.
And in which direction this wave is moving? It is moving in this direction here. Right now, it is moving in this direction. And then you see that these are the particles. Aren't these the water particles? Yes or no?
Yes, sir.
So they are moving perpendicular to the direction of the movement of the wave. The wave is moving in this direction and the particles are moving like this. They're moving perpendicular. They go up and they come down, goes up and then goes down like this. So they are moving in a perpendicular fashion. Is that thing clear to everyone what I'm trying to say here?
Yes, sir.
Yes, sir.
If anyone is left who is not getting it, any confusion, please let me know. So that is the case of the transverse waves. Okay. So particle motion is perpendicular to the direction of wave. Wave is moving in this direction and the particles of it is moving perpendicular like this. They're moving perpendicular like this. So at any given point, this particle is perpendicular, this particle is perpendicular. All of them are perpendicular to the direction of the movement. Okay. Further, when they are above this line now, that is called as crest. And this is called as trough. That is crest and this one is trough. Okay. So hope you guys are getting it. Another example, like ripple is an example of transverse wave. Light is also an example of the transverse wave. Light or the ripples in water, these are examples of transverse wave. Now, when you look at this image here, look at the second image in this. Here you are getting to see that the particles are moving parallel to the direction of the movement of the wave. Wave is also moving in the forward direction. Like in the case here, in the case of the sound, what we are getting to see that the particles are also moving in this direction and the particles are moving in this direction, isn't it? They're moving like this. They're vibrating in this manner. Are they moving up and down or are they moving forward and backward? Are they doing to or fro motion or upward and downward movement?
They are doing forward and back.
Good. And the sound is traveling in the forward direction, isn't it? Sound is also traveling in this direction now,
Yes, sir.
right? So when we look at the movement of the, like, say, for example, this is the, say, for example, that this is the particle that is moving and this is the sound. 1 minute. Say that this is the particle that is moving and this is the sound wave. So the sound wave is moving in the forward direction and the particles are also moving in the backward and forward direction, to and fro movement. So aren't they parallel to each other?
Yes,
The
sir.
sound is moving in the forward direction and this is the particle which does a to and fro motion, forward, backward, like this. So that is the case of the longitudinal wave, in which we get to see that the particles of the medium, they move parallel to the direction of the wave. So when the particles of the medium will be traveling parallel to the direction of the wave, that is an example of a longitudinal wave, and they will be doing successive compression and rarefactions. Okay, na? That is the example of this. You can look at the example of the slinky here. This spring, when you will be dropping a spring from height, you will see it will go up and come down, go up and come down. So that too is an example of a longitudinal wave. Hope everyone have understood this. If there's any question in this, please let me know. Yes. Is the
No.
difference between transverse wave and longitudinal waves clear?
Yes, sir.
Oh, good. So do tell me, in the case of the transverse waves, the particles of the medium will be moving parallel to the direction of wave, or will it be moving perpendicular to the direction of the wave? Should I repeat? Are you saying that in the case of the transverse waves, the particles of the medium, they move perpendicular to the direction of the wave, or they move parallel to the direction of the motion of wave?
Perpendicular.
Okay, what about others?
Perpendicular, sir.
Okay, so Khadija, you also got it?
Yes,
So Roni, so that is the case here. They will be moving perpendicular, but in the case of the longitudinal, they move parallel. Okay, no? Okay, hope that is clear. Examples of the transverse wave. Can you guys give an example?
Light
Light and ripples on water,
yes, sir.
right? Ripples on water. Okay, and that of the longitudinal wave. We just have learned about this. The chapter is based on it. That is simply sound, isn't it? Sound is a longitudinal wave, no?
Yes, sir.
Okay. Now there are some terms associated with the sound. There are a few important terms which we are going to learn about. Okay. So these are frequency, time period, and the amplitude of a sound. Okay. To understand this, there are few basic things which you guys would require to learn. Then we are going to continue. Like, you need to learn about the oscillatory motion and then the oscillation. I suppose some of you would have learned about this in your previous classes. Let's first of all learn about the oscillatory motion. Oscillatory motion is like whenever an object does a to and fro motion. Like, for example, when you are sitting on a swing, so you go forward and you go backward, you do a back and forth motion. For example, when you suspend a spring from your hand, when you suspend a spring, so the spring will be moving down, it will be moving up, so that will also do an oscillatory motion now. So whenever an object does a to and fro motion, so that object is said to be doing an oscillatory motion. We have the common example of pendulum also. Pendulum also does an oscillatory motion, isn't it?
Sir, its heartbeat is also oscillatory motion.
Heartbeat. We can say that it's a periodic motion. Heartbeat is a periodic motion, and I think it can be said as oscillatory motion because it does backward and forward motion. Okay, no? So yes, I think we can consider this. In fact, it is a periodic motion and as well as oscillatory motion. because for it to be a periodic motion, it has to repeat after a regular interval, right? Now, periodic motion like the rotation of the earth, revolution of the earth, or the movement of the hand clocks, or the minute or the second clock, all of it is a periodic motion. And oscillatory motion, the heartbeat will be a oscillatory motion also. Okay, so it can be classified as that. Okay, Abdullah. Oscillatory motion, the examples which I gave, suppose you have attached a spring to a support and you have attached some weight to this, or you just pull it from here. So it will be going downward, and then after you will be releasing it, you will release it, it will go upward. So isn't it doing a to and fro motion, forward and backward motion?
Yes, sir.
So we have the example of the spring, or we have the example of the swing also. Swing also does a to and fro motion. No? Swing also does a to and fro motion. So when an object moves in a to and fro motion, it is said to be doing oscillatory motion. Further, if you were to talk about another important term here, that is oscillation. One another example, you have the example of a spring, swing, and the third example, take the example of pendulum also. Okay, pendulum. Talking about oscillation, so oscillation is said to be the movement of the object from one point to another in a fixed interval of time. So one oscillation, we will see that it is the movement between the two end points or two extreme points of the motion of the object. Say for example, consider the movement of the simple pendulum. Let us understand how it will be doing the movement. So suppose you have a simple pendulum and we are going to attach it to a fixed support. So we have taken a pendulum like this. What do we call this structure? We call this as bob of the pendulum, right? Now
Yes, sir.
this is the mean position. This is the mean position where it is resting. Now you push it. Okay, now you are going to push it, so it will do a movement and it will go to the extreme position. It will go to some distance and then it will stop. So that will be called as extreme position. So we can call this as extreme position A. Extreme position A, and then from here it will travel to another extreme position. That we can call this as extreme position B, right? So the motion of the pendulum that we are seeing here, like if you were to talk about oscillation of this pendulum, so it will be moving from one extreme position to another extreme position, and then it will return back to the first extreme position. So that will be called as the one oscillation of the pendulum. Basically, when the bob will be moving from one extreme position to the other extreme position, and then will come back to the starting position. So that will be called as one oscillation done by the pendulum. When it will start its movement from one extreme position A, and it will travel to the other extreme position B, and then return back to A. That will be called as one oscillation. Let me just highlight this thing. It will go from here to here, and then it will return from here back to here. It goes from extreme position A towards B, and from B returns back to A, and it will take a fixed amount of time to do this. A fixed interval of time will be required to do this particular movement, and this will be called as oscillation. Is that thing clear to everyone? What is oscillation?
Yes, sir.
Shakrika, Khadija, Abdullah, Roni, everyone got it?
Yes, sir.
Let me write an important definition for this. So when an object goes from one extreme position to another extreme position and and returns back to the previous position in a fixed interval of time. In a fixed interval of time, then it is called one oscillation. Then it is called one oscillation. Hope it should be clear to everyone, right? So that is the concept here. Further, there's another concept which we have to learn, that is about the frequency. In order to learn about the frequency, first of all, frequency will be basically the number of oscillation that an object will the number of oscillations an object will take per second. The number of oscillation that an object will do in 1 second will be called as its frequency. Will be called as its frequency. Say for example, if in 10 seconds, say for example, if in 1 second it does 5 oscillation, so the frequency of this pendulum will be 5. It will be 5 hertz. Or if in 1 second it does 20 oscillations, so the frequency will be 20 hertz of this pendulum. You guys getting it? What I'm trying to explain here?
Yes, sir.
So frequency is basically the number of vibrations or oscillations that is completed by an object in 1 second. Okay, no? In 1 second. And frequency is, to calculate frequency, we calculate in the following manner. Whatever is the total number of oscillation and the total time that is given, you will be able to calculate frequency in that following manner. Okay. Suppose, for example, an object is oscillating 20 times in 5 seconds. It does 20 oscillations in a matter of 5 seconds. So frequency will be 20 upon 5, that will be 4, and it will be represented by hertz. The unit of frequency is hertz, and in short, it is represented as capital H and a small z. That is one thing. Now you might notice this formula here. I have written another formula here. Okay. Frequency equals to 1 upon time period. Frequency equals to 1 upon time period. This is mu, and in a short form, it is frequency is represented like this. But you guys just understand that this is capital F. So frequency here is inverse of the time period. Inverse of the time period. What do I mean to say that? Suppose, take the example of that simple pendulum here. Take the example of the simple pendulum. So there is another concept. While you have learned about the simple pendulum, you guys might have learned about the time period. Have you guys learned about time period in context of simple pendulum or not?
What, sir?
Time period.
Yes, sir.
So time period is basically the time taken to complete one oscillation. That will be called as time period now. The time it will be taking to complete one oscillation, right? So that is called as time period. Suppose I give you a question that in terms of the time period, let us say that there's a simple pendulum, okay, and it does 10 oscillations in 5 seconds. In 5 seconds, we have to find the time period of the pendulum. So time period, let me just define this so that you will be able to solve this. What we say, the time taken for one complete oscillation of a sound wave, or basically of this pendulum here, I mean to say. So the time taken for one complete oscillation of a body is called as the time period. The time that it will be taking to complete one oscillation is called as that will be the time period of the body. Correct. So as per this question, it is saying that 10 oscillations are done in 5 seconds. You have to calculate the time period. And for time period, let me just tell you once again, as I said, that it's basically the time taken to complete the oscillations. So time period will be simply, what is the time taken here? It is 5 seconds.
5 seconds.
And the number of oscillation done is how much?
10.
10, no? Right? So that will be how much? 0 0.5, 0.5 second, isn't it?
Yes, sir.
Got this, everyone. So that is the case here. Okay. So if a pendulum does 10 oscillations in 5 seconds, so thereby the time period is 0.5 second. Now, if you were to compare it with the frequency, for frequency, what we have, the formula to find the frequency, it is the total number of oscillations upon the total time that it takes. As for the time period, what I have told you guys, as for the time period, see here, time period is the total time upon total number of oscillations that is done by the body. Total oscillation that is done by the body. Compare those two formulas side by side. In the case of this one, in the case of the frequency, it is number of oscillation upon total time. And in the case of the time period, it is the opposite. It is total time upon total oscillations. Aren't they opposite of each other? Isn't time period basically reciprocal of the frequency?
Yes, sir.
I think some of you are getting confused in this. Let me write both of them side by side. For frequency, I have written it is number of oscillation upon total time. And time, it was total. For time period, it is T here is for time period. It is total time taken upon total number of oscillations that is done by the body. So they are opposite of each other. You can see the the value in the numerator and denominator, they are reversed here. So frequency, can we call it as 1 upon time period simply? Can't we call this like this? Frequency is simply 1 upon time period. It's the opposite of the time period here. When you're going to reverse the value here, so number of oscillation after being reversed, reversing this, number of oscillation will go to the numerator and this total time will come into the denominator. Will that not become the formula of frequency? Let's reverse this. So after reversing, T will become 1 upon T. Right, Chakrika, Abdullah, Khadija,
Yes,
everyone. And this will
Yes.
be number of oscillations upon the total time. And match it from here. What is it equal to? Basically, number of oscillation upon total time. What do we call this? Frequency, isn't it?
Yes, sir.
So in place of this, can I write frequency? Frequency equals to 1 upon time period.
Yes, sir.
So this is what has been written here. You can simply calculate frequency by reversing by this formula as well. If time period is given, so you can simply find the frequency. Or if time period is not given, or oscillation and total time taken to perform the oscillation is given, okay, number of oscillation and total time is given, then you can use this formula. So there are two formulas to calculate the frequency. In the time to come, we will be learning about that in detail. Chakrika, is it clear to you? Roni, Gauri, everyone understood the relation between frequency and time period?
Yes, sir.
Okay. And we have learned that it is expressed in hertz and the unit, it is represented in short form as capital H and small z. Further, a frequency of 20 hertz, it means there is 20 oscillation in 1 second. Whenever we talk about frequency, the unit is just 1 second. Okay, na? It is not 2 seconds, 3 seconds, not like that. Or if an object oscillates or vibrates 80 times in 1 second, then its frequency will be equal to 80 hertz. Okay. So say for example, if an object oscillates to 196 times in 1 second. What will be its frequency?
What, sir?
If an object oscillates to 196 times in 1 second, what will be the frequency of that object?
196.
Only 196. What about the unit?
HZ.
Hertz. So that is exactly 196 hertz. No? Okay. Now let's change the question here. Now let's see that
So what is the full form of headset?
that is HERTH, TZ. Okay, no, this is hertz. You're asking for the full form of this one. This hertz.
Yes.
Hertz was the name of a scientist actually. Okay, no, hertz was basically the name of the scientist. Okay, so it doesn't have any full form. Okay. Now, what if I were to change the question? Let's change the question. Hertz was basically he was a scientist who basically he did some demonstrations on how electromagnetic waves will be traveling, and he basically proved the existence of the electromagnetic waves. Okay.
Yes.
So like in order to honor his legacy, in order to honor him, basically the unit of the frequency was named as hertz. Okay. Now my question was, now if suppose the time here is 4 second, if it is 4 second, then what about the frequency? Will it still be same or will it be different? Using the given different, na? Using the above formula, this formula, number of oscillation upon time, calculate the frequency. Answer in the chat box. Well done, Chakrika. Good. The unit could be appropriate, not a small h, capital H, and then a small z.
Yes. Sir, which ID we have to answer?
On this one, hope it is visible.
Okay, sir.
Yes, well done, Khadija. Everyone have noted down the question now. So if you have noted down the question, I'm switching the slide to this one here. See, if you were to look at the following images here, look at this image particularly, this one and this one here, or just look at this. Look at the lower two images here, this one and this one here. The number of frequency in this one is more, and the number of frequency in this one is less. The time period is basically, let's say the time period here is 1 second, and here also the time period is 1 second. The time is 1 second. Which one is doing more movement? Which one has having more frequency? Clearly this one.
Yes, sir.
This one has less frequency. Okay. So a sound wave that will be having a higher frequency, in which the number of waves produced in just 1 second will be more, so it will be having a higher pitch. Generally, women have a higher pitch, and a man would be having a deep voice. Okay, now in this you will see that the number of waves produced in 1 second is less, because of it the pitch is low and they have a deeper sound. Others done with the question or not?
Done, sir.
Some of you haven't answered it. That's why I'm asking. So it is 196 upon 4. That is 49 hertz simply. Okay, no? So that is the frequency here. Okay. That is one thing. So the frequency will determine the pitch of the sound. The pitch of a sound will be determined by its frequency. A higher frequency sound is perceived as high pitched. Okay, now a sound which is having a high frequency, its pitch will be high. While a sound wave whose frequency is low, thereby it will be having a low pitch. It will be having a low pitch. Getting it, guys? That is one thing. Now, as we are talking about frequency, our ears can hear the sound which has a frequency of 20 hertz, which has the sound waves that has a frequency of 20 hertz to 20,000 hertz. We can hear that sound only. So the audible range of the sound for our ear is 20 hertz to 20,000 hertz. We can hear the sound waves of 20 hertz to 20,000 hertz only. If there is sound that is having a frequency less than 20 hertz, or if a sound is having a frequency more than 20 hertz, that will be inaudible to our ears. We won't be able to hear that. Okay, now? So basically, there are some animals that will be able to hear these sounds, and different animals have different hearing ranges. Different animals have different hearing ranges. So this is called as the this is the audible frequency range for the human ear. Audible frequency range. Okay. Now you guys would have learned about the concept of ultrasound, right? You would
Yes,
have learned
sir.
about the ultrasound now, right?
Sir.
Ultrasound, or basically sonography or the ultrasonography, which will be using high frequency sound waves to get the picture of the inside of the body. So that ultrasound is this concept. It will be using the high frequency sound waves. Basically, the sound waves that has a frequency more than 20,000 hertz, they are called as ultrasound. They are called as ultrasound. So are you able to hear the sound, that sound, this ultrasound, when you go to a when someone goes to get an ultrasound done or a sonography is done? So do they hear the sound that is produced? Although the sound is very loud, I mean to say it is having a frequency more than 20,000 hertz, but we don't hear that now. Getting it, everyone? What I'm trying to say?
Yes, sir.
That is one thing. And it will be helpful in diagnosing different kind of diseases, right? Particularly during the case of pregnancy, in order to check the growth of the fetus or the health of the fetus, the sonography is done right now. Many times when biopsy will be done, so thereby the sonography will be helpful in that. Ultrasound will be helpful in that. Okay, now biopsy, you guys done understand what is biopsy? BIOPSY. This medical term biopsy. No? Biopsy, like whenever some cells or some tissues are removed from the body in order to study it, if there is some damage, if there is some risk of disease, that will be called as biopsy. Basically, like under the microscopes it will be studied, and the cells will be studied, cells will be analyzed to check if there is some disease. Okay, now so certain suppose someone has undergone a biopsy, so what the surgeons will do, they will take out some portion of the body, I mean to say they will take some tissue or some cells from the body. Tissues will be taken from the body and it will be examined under the microscope to study if there is some issue in there. Okay, getting back to the concept here. So we have learned about ultrasound, then we have infrasound also. Ultrasound and infrasound. So frequencies that have lower the lower frequencies, which is the frequency that is lower than 20 hertz, we call that as infrasound. Infrasound. So both the infrasound and ultrasound are not audible to our ears right now. That is one thing. Okay, while talking about these, the infrasound and the ultrasound, although it is not audible by us, but certain animals can hear the ultrasound and the infrasound, right? For example, dogs or the bat or the dolphins, they are capable of hearing the ultrasound right now. So they are able to hear the sound that is having a frequency more than how much?
Uh,
Anim
20.
20,000 20,000 hertz, right? So namely examples of the animals are dogs, bats, or dolphins. Then you have animals like elephant, animals like giraffe. They are capable of hearing the infrasound, a sound that is having a frequency less than 20 hertz. Okay, now sometimes 20,000 hertz, it is also written as 20 kilohertz. Or basically the thing is 1 kilohertz is equal to 1000 hertz. 1000 hertz. So in short, we can write this 20,000 kilohertz as 20,000 hertz as 20 kilohertz. Okay. So hope this much is clear to everyone. Now frequency will determine the pitch of the sound. The frequency will be determining the pitch of the sound. More the number of frequency, more is the higher is the frequency, the pitch of the sound will be more. Lesser is the frequency, the pitch of the sound will be less. So that is one thing. Hope you guys are getting this much. Now we have another concept, time period, as we were discussing about it moments ago. So we learned that in the case of the sound or in the case of any object, particularly we are learning about sound. So the time taken by an object or the particle of the medium for completing one oscillation or vibration is called the time period. It is represented by capital T and the SI unit is second. In the case of the sound wave, what we can say? We can say that the time taken for one complete oscillation of the sound wave, the time taken to complete one complete oscillation of the sound wave is called the time period. Right now? Is that much clear to everyone so far?
Yes, sir.
Okay. So we have learned about few important things here. In the next class, we will be continuing with the concept of amplitude and we'll be doing some numerical problems on this. Okay. Before we end the class, I have few questions from you guys. You guys give three examples of oscillatory motion.
Pendulum,
Okay, good. And yes, pendulum and the motion of the swing
yes, sir.
and the motion of the
There's
spring.
a heartbeat.
Heartbeat. Exactly. Okay, na? Okay.
Like musical instrument strings, like when you struck them, can they be also counted as oscillatory motion?
Exactly. They can also be called as oscillatory motion. Like the membrane of the drum or the string of the guitar, they also do the oscillatory motion. Okay, no? Okay. By the way, you guys think of this, like whenever we hear a sound, so does any part of our body will be vibrating whenever we hear some sound? Is there any part in the body that vibrates?
Our eardrums.
Our eardrums, exactly, no? Very good. So our eardrums will be whenever we hear sound, basically due to the vibration of the eardrum, we'll be hearing the sound. Good. Now you guys tell me if like if you were to take an alarm clock and if you were to put it in a vacuum jar, will you be able to hear the sound from the outside?
No, sir.
Obviously, no.